So I'll talk about the ongoing return project, and it's about monitoring tropical forest recovery capacity using a lot of satellite data. And the project is ongoing and is also a use case, part of it within C-Scale. But we'll here illustrate with this presentation how C-Scale will be useful for us, or is useful for us. So I'll start the talk and then Milutin will continue. So it all started, the return project at least, started with a publication in Nature Climate Change, where we looked at the resilience of intact tropical forests. And we actually mapped resilience across the pantropics of these tropical forests using long time series of coarse spatial resolution data, like MODIS data and GIMS, etc. But what we wanted to do with the return project, which is an e-science advanced scientific discovery project, we wanted to look at the disturbed forest. So not only intact pantropical forest, but also the disturbed. And you have many tropical forests that are quite disturbed with due to illegal forest harvesting or deforestation. And specifically, we wanted to apply a tool that we've developed called BFAST. That is an open source tool, R, programmed in R language, for detecting breaks within time series. And here you see an example on time series from satellite MODIS, where you can really see trends in planting of a forest and regrowth, harvest that they're being detected by breaks, and then the following recovery, so regrowth of those trees. That's the citation. Also, the code is open source, available via GitHub and still being developed. And within return, we wanted to specifically focus at the recovery speed after disturbances to get a direct measurement of resilience of those tropical forests. And a postdoc, Wanda, the case maker, started on this project looking at multispectral data, so Sentinel-1, Sentinel-2, sorry, and Landsat 8. And for that, she started off developing a software tool called Make Data Cube together with the Dutch eScience Center. And I'll explain a little bit more in the next slide about that. And the second part of the presentation will be explained by Milutin, who is a postdoc still working on return within the context of return, focusing at Sentinel-1 and radar images. And here I'll explain about this tool because it's quite relevant within C-Scale. Make Data Cube is basically a tool that uses open source force software, which is a software that can pre-process satellite data like Sentinel-2 and Landsat, and that we basically used via R language to parallelize and enable that to be applied on a Spider platform. So you have Spider is a surf computer cluster that is available, and that's where basically the Make Data Cube software tool can be applied on. And so it enables the processing of large amounts of Landsat data to create data cubes basically that are analysis ready. And that is quite handy for us because we wanted to create a data cube for the whole of the Amazon, for Brazil, for example, via surf infrastructure. And that's immediately an example of how the C-Scale project is useful for us. And that code is also of Make Data Cube available via GitHub. And now I leave the floor to Milutin. Milutin?
Yes, thank you,
okay.
Jan. I just have to take over the control.
Yeah.
Milutin, it's Christian.
Oh.
Okay, so now I have control of the presentation. Thanks a lot, Jan, for intro. And yeah, so yeah, as explained, so my work is more focused on monitoring tropical forest recovery capacity using radar images. yeah, our study site is South America, and what we are doing is looking at the collection of Sentinel-1 images, and then we are extracting the time series from Sentinel-1 images and looking at the disturbance events and extracting further different features within a time series, and then we map them either spatially as recovery maps or derive some statistics for certain regions. And our code is mainly based on Python, and we are also dependent on Snap software for data pre-processing. Yeah, so that's a brief overview of the work. I'm just trying now to move to the next slide. Okay, so I think now it works. Yeah, and here we see a Sentinel-1 backscatter time series where we have some stable history period and then a disturbance and recovery event. And one of the features we extract is a magnitude and total time. Those are the two very basic features. And then we derive some statistics over that. But in reality, not of all time series are like ideal disturbance recovery time series. We of course have a no change time series with no change, or time series that have a disturbance event in a history period. And also we have a time series that have a disturbance event but no signal recovery. Yeah, and those are all different kind of categories that we take care of and map spatially. You can see here in the middle an example of how those categories are spatially mapped. And yeah, with this slide, I wanted to show you our current workflow. So what we are basically doing, we start here on the left side with for a certain area of interest, we introduce our spatial grid. And so those are basically independent tiles that we are introduced to make a parallelization of our code. Then we go to the Google Earth engine and prepare the Sentinel-1 analysis ready data there. Our colleague from Wageningen developed, and actually there is a radar a forest monitoring team at Wageningen University. They developed a set of code for a Google Earth engine, and also they developed the code for providing analysis ready data. This is what we are exploring currently. And then we have some extra code that combines this data with existing disturbance maps, and also doing some post-processing of this data to prepare a kind of a data pool, yeah, that we keep in Python in the form of X-arrays. And this data pool is then a base for another piece of Python code that we use to standardize this to the 6-day Sentinel-1 data cubes and for disturbance recovery features. So we basically extract all those information and keep again as a more standardized data cube, again in a X-array data structure, and this is finally the basis that we use for mapping, analysis, or just a simple visualization. And what is our current goal and what we are working now on is to replace this part, so the Google Earth Engine part with the surf. So we are very much interested to have our workflow and code and analysis open and reproducible. And we think that at Surf we can facilitate that much better. And another part of this workflow that we would like to replace is this a bit of complexity of the right side from going from analysis ready data to the data cubes. Yeah, so and this part we would like to replace with OpenEO API, and yeah, so that basically can help us to go from the pre-processed satellite images to the data cubes. Yeah, and regarding the OpenEO, Jeroen will definitely say much more about that in next presentation. But from our side, we already have a really positive experience with this API, and we were able to work on two different backends with two different user-defined codes, so in Python and R. We were testing that using the BFAST code in Python and R, and for detecting the breaks. And our first experience was really positive, and we were able to use successfully OpenEO and scale the analysis on those backends. Yeah, so about the current challenges and solutions, yeah, so definitely the big challenge for our use case is to obtain Sentinel-1 analysis ready data over the large area. Yeah, so for the whole Amazon rainforest. And currently there is a committee on Earth observation satellites who introduced definitions and requirements for analysis ready data, and this is a flattening gamma. And it's simply the flattening gamma involves several processes that are time consuming, and it's quite a challenge to provide this data over the large scale. So we are looking at a different solution currently, and one of those is to obtain a Sigma Knot product from EODC, Earth Observation Data Center, and this is through the collaboration on the C-Scale project. Yeah, but this kind of data would require additional restriction of our analysis to flat areas. Another solution that we are looking at is that we try to process and prepare a flattening gamma directly at the Spider cloud computing, and together with the SURF, we are working on testing a snap workflow and processing directly on Spider to derive the flattening gamma. And another solution also that we are considering is obtaining the flattening gamma product through VITO Terrascope platform. We already had a small use case on the Terrascope platform using OpenEO Python user-defined functions. And the advantage of this approach is that the Terrascope platform and VITO has a direct access, a link to the synergized Sentinel-1 analysis ready data that could be potentially used in that approach. And of course, having all those different data providers, we end up usually with a different data structure. And one of the things that shouldn't be overlooked is that the code, user code, is often has to be adapted to this particular data structure. And this is just another challenge that we wanted to highlight here. Yeah, in a conclusion, yeah, we are very much interested in providing open and reproducible research on video Earth observation data, and we are definitely sure that SURF can facilitate this need for us. But till that end, it's definitely we need to bring more and more analysis ready data close to the infrastructure. and either using our own workflows through the SNAP or make data cubes or through the C-scale initiatives or other data providers. And another important thing is that the data should be exposed to the users on easy and standardized way. And a way forward for that is definitely OpenEO that can help a lot in lowering barrier in accessing and scaling up the analysis. And finally, what I would like also to underline, there are also other challenges beyond analysis-ready data and data cubes. They are arriving very soon. We have a lot of field data and other kind of sample data, yeah, like spaceball LiDAR. So you can see an example on the right side. So those data are basically a sparse samples. So they are sparse data, not efficiently represented as data cubes. But anyway, those data should be used together with data cubes close to the infrastructure for scaling up and providing and training the Sentinel-1 data and providing machine learning models. And we see that that SURF can be really a facilitator also for these next steps and going one step further for merging different kinds of data at the SURF infrastructure. Yeah, thank you very much. That's all from my side.
Thank you very much, Jan and Milutin. The hybrid setting worked perfectly for the presenters as well. Are there any questions from the audience, maybe? Yes, there's one.
I have two questions, but one is probably more for Jeroen on the OpenEO. No, stand in the front. Right. I need to remember my questions. Thanks, Milutin, and thanks, Jan, for your presentation. I had a question about the three solutions that you presented in your previous slide. In terms of the different processing pipelines that you're going to try. Are there ambitions within the context of this project to test the performance of those three different solutions? Yeah, exactly.
Yeah, thanks for the question. So currently, what we would like, what is our first aim is to really ensure the data at the first place. And yeah, so I'm not sure if we will have enough time and resources really to test different solutions and what is the most efficient and yeah, advantages and benefits. But it's definitely a good idea and a relevant thing to consider as a potential, also as a potential use case. Yeah. So but at the moment, it's really due to the capacity limitations. It's really difficult to focus on all those things deeply and thoroughly. Yeah. So.
Understood. Thanks, Milutin.
Okay, thank you. It's